download it and check it out. I also posted these slides yesterday, but this morning I realized that a couple of slides had not been updated properly. So if you downloaded it before about 20 minutes ago, you might want to just double check and update the gravity loading slides. I'll point that out when we get to it. So before we get started, homework 10 due tonight. Any questions? All right. Let's see. Oh, all right. So yeah, homework 10 due tonight. Today, I've got this slide started off with a quick FEA recap, right? So finite element analysis is going to be the topic of next week's lectures regarding frames, but also finite element analysis is part of what you're going to be doing in the final project, except you're not going to be doing hand calculations for FEA. You're going to be using visual analysis, right? So just as a reminder, visual analysis uses finite element analysis to generate its results. And then, yeah, I'll introduce the final project. Friday, we will continue talking about the final project, talking about analysis and design approaches. I will probably also be doing some visual analysis demos to show you a few additional things that we haven't yet covered explicitly that will be relevant for your final project. And then if there's time, we can do a little bit of review in advance of the third exam. So if you have anything specific that you would like me to touch on Friday with regard to the exam, please email me in advance to let me know, and I can prepare something to speak to that end. Otherwise, if there's time, I'll just touch on a few things that I think would be beneficial, right? So, and then next week, of course, we have the exam on Monday. Wednesday and Friday will be the last two lectures of the semester, and those will be regarding finite element analysis for frames. The week after that, we meet on Wednesday. I'll point it out in the schedule when we get back to the skeleton notes, right? So we are required to meet during that time, even though we don't have a final exam. Now, your final project will be due Thursday of finals week. Technically, I should be having it due on Wednesday when we're scheduled to have our final exam, but I decided to extend that a little bit to Thursday morning, right? So we'll talk more about that. It's going to be due at 9 a.m. But we will meet on Wednesday. I have some interesting lecture material and stuff prepared. So we probably won't take up the full hour and 50 minutes, but it'll be an interesting lecture. And then also there will probably be some extra credit associated with that. So please plan on attending that Wednesday the 13th. All right, so a quick finite element recap here. All right, remember this grid, and I've got a few things filled in for you. So it would be, probably good practice for you to print this slide and work on filling in the blanks. All right, I do have the solution posted on the next slide for you. So this is broken down in terms of the types of structural elements that we have discussed so far in this class. Right, we talked about beams, single axis axial force systems, and then trusses. So the next level would be frames, right, which we'll talk about later, and that's going to expand the number of degrees of freedom per node to 3 degrees of freedom per node, right? So that means your matrices are going to be a lot larger for frames. But this is all that's relevant for exam 3, right? We won't even talk about frames until after exam 3. All right, now on to the final project. As I mentioned, the due date is Thursday, December 14th, no later than 9 o'clock a.m. This is a firm deadline. I will not accept late submissions. So my recommendation is that you aim to complete it by Wednesday of that week, and then You'll have a little bit of a buffer in case something unexpected comes up. But please give yourselves plenty of time to complete this project, right? You have a little more than 2 weeks, and that is plenty of time. Almost every semester that I've assigned this project, at least one person has completed it and submitted it within 1 week, and also done a good job on it. So it just kind of depends on your time management and everything that you have going on, but please don't wait to start it. Now, the premise of this project is, as you can see, a 3-dimensional building that is going to be constructed of a rigid steel frame, meaning a moment frame system, all right? And we are simplifying this to say that all the beams and all the columns of this frame are going to be the same size. Now, that's not very realistic, but for the purposes of this project, we want to keep it manageable within a 2-week span. So we're going to make that simplification. Now, as I mentioned before, even though it's presented in the context of a 3-dimensional structure, you only need to analyze a single 2-dimensional frame, right? So the frame that's outlined in bold is the one that we're going to focus on. You can see that based on the symmetric dimensions in this direction, this frame will have the same tributary width as this interior frame, right? And so those interior frames will represent the most severely loaded elements in the system. So we only need to look at one of those frames for our analysis. All right, so the overall tasks include conducting approximate analysis, and then that's going to include the vertical, right, approximating the beam moments due to vertical loads, approximating column axial forces due to vertical loads, and then approximating internal shear moment and axial forces due to lateral loads using the Portal method for all beams and columns. Once you have conducted all of the approximate analyses, you will superimpose those results. We talked a little bit about that last time. And then use that information to identify what is the most severely loaded beam and what is the most severely loaded column. With that information, then, you're going to use those 2 most severely loaded elements to choose an initial size for your building, right, for the beams and columns. So we're going to be working with wide flange sections. There are a bunch of tables that are attached to the project document, which we'll look at later on today. And then based on your initial design, which was selected according to your approximate analysis results, you're going to use that size in your visual analysis model, right? Because as you know, in visual analysis, in order to look at any results, you have to assign a section size to it, right? So we can talk about that in a moment as well, a little bit more. And then you're going to use visual analysis to verify whether or not your initial design section will work. If it does work, that's great, but check to see if you can get a smaller size to work, right, or a lighter shape to work. And then if it doesn't work, if your initial choice doesn't work, then size up until you get the smallest size member that can work for everything, right, or the lightest weight. I'll talk about that in a moment too. You have a choice as to what your target is. And then you're going to submit a report that summarizes your findings, etc. We'll talk about that in more detail later as well. And everything should be submitted to Gradescope, again, no later than 9 a.m. on Thursday. That date is incorrect. That was last semester's deadline. So, Thursday, December 14th is the deadline. Make sure that you tag pages appropriately. So we will continue then with the project details here. All right, so gravity loading. This structure is intended to be a lightweight or a light manufacturing building. And so it's going to have some significant gravity loads, right? Significant dead and live loads. The roof deck is not one that can be occupied, so our roof live loads will be the standard 20 PSF. It says the roof space includes a 64 by 88 area at the highest level, the 39-foot elevation, and then a 24 by 88 area at 15 feet elevation. So the load case that we're going to be using in this is from Allowable Stress Design, and it's going to be this one right here, right? Since we're not considering snow or rain or earthquake loads, that's going to simplify down to just dead and live and wind. So with your live loads, in this case, since this is the only load combination that you're considering, it's okay in this case to include your roof live loads and your floor live loads in the same load case. And that's mostly relevant for visual analysis. All right, so we'll talk more about that later. Now, the exact loads in pounds per square feet are provided here for you. So this would be what you would obtain from the ASCE 7 tables. So for the floor, your dead load is 150 PSF, roof 100 PSF. Assume that this includes all self-weights. So you don't have to think about self-weight in your hand calculations. You don't have to worry about, well, I will say you should change the setting in visual analysis to not include self-weight, right? Because remember, that is the default setting for the dead load case. So make sure that you deactivate that default setting so that it does not include the self-weight. Otherwise, you won't be able to directly compare your visual analysis results with your hand calculations, and that's the point of this project. So assume all self-weights are included in those values, and that's why they're a little bit higher too, right? So, and then for live loads, we got 100 PSF for the floor and 20 PSF for the roof. We're not going to reduce any live loads, so just use those values. And then for wind loads, we'll talk about that in a moment. Again, having all those, all the self-weights included and not reducing live loads, that's more simplifications. Although for this case in particular, since our live load is 100 PSF, I think that's the cutoff where the code says it's not reducible, or at least in certain situations. So, but regardless, that's a moot point because we're not reducing live loads. All right, so with your gravity loads, right, as you noticed, they are provided to you as surface loads. So your first task is going to be to condense them into line loads that are acting on the beams in the frame that you are considering, right? So you're going to calculate that tributary width for that frame and calculate what the line loads are on all of the beams in that frame. So that should probably just be the very first step that you take in this project, because you'll need it for your approximate analysis calcs and for your visual analysis. For wind loading, all right, the wind loads, as I mentioned last week, are provided to you as point loads acting at beam column joints. So we're only going to be considering wind in this direction. You got your windward forces, right, shown here, and those are, as you can see, increasing with height. Your leeward forces, right, is not completely accurate as to how it should be. I think this is a typo here, because this value should be a little higher, but regardless, we'll just go with this. That's fine. We'll just go with what I put out there. And we got 20 kips at each node on the leeward face. The roof values are acting upward, right? That's suction, so they will counteract the effects of the gravity loads in those columns. And as I mentioned last time, the roof wind loads, actually any of these wind loads, the roof wind loads is what I'm focusing on here. All right, so those roof wind loads, because they are just acting at the columns, they will not affect the forces in the beams, right, for your approximate analysis. So we are simplifying that as well, but that is a conservative simplification. All right, another thing that I want to emphasize is that it's important throughout your approximate analysis and visual analysis that you keep the lateral wind loads separate from the vertical wind loads. All right, so one reason is because the portal method is only for lateral loads. If you include those vertical wind loads in there, it's going to mess everything up for you. So please don't do that. Another reason is because we want to, once you have completed your visual analysis, all right, one of the things that you're going to be doing is reporting the results image of the frame only due to lateral loads. All right, so even in visual analysis, you want to create a separate load case for your lateral wind loads and your vertical wind loads. We'll talk more about that later. Let's see, I already talked about this, right? We are conservatively neglecting the effects of wind on the roof beams. And then you'll also see in this image the node numbering and column and beam labeling that I have used. And I would like you to use the same numbering and labeling system in your work so that it is easy to follow. And that includes visual analysis, all right? So just make sure that you are careful in your construction of the model. All right, so I highly recommend, as I mentioned earlier, that you give yourself plenty of time to complete this project. Start by reading through the project document, right? Read through it and then read through it again, right? Make sure that you read it carefully so that you understand everything that is expected. The majority of the relevant lecture material has already been delivered. We will wrap the rest of it up today and then on Friday as well. So if you need to, right, you can always review the recorded lectures posted in the last couple of weeks that are related to the things that you need to complete in this project. So if you want to get started, well, you do want to get started, I suggest any of the following points for beginning, right? It doesn't really matter if you do any one of these first, second, or third, or fourth. So you can start with the portal method, or if you're sick of the portal method from homework 10, you can take a break from that. You can do approximation of beam moments due to vertical loads. You can do approximation of axial column axial forces due to vertical loads. So that's something that you haven't actually practiced yet, right? These two were included in homework 10. This one we covered in class on Monday. Or you could start by building the visual analysis model. You don't have to wait until your initial design is completed or your approximate analysis, right? The only thing that will be left to do then is to assign the appropriate size based on your initial design. But if you feel like it, go ahead and set everything up for modeling that frame. Make sure that your model is stable, right? You can get the node numbering and the column and beam labeling correct in there. Play around with it, make sure that you understand what views are going to be expected in your report and how to obtain those and things like that. So we will talk about assigning load combinations in visual analysis this week. Probably on Friday is when I'll get into that because that's one thing that we haven't done yet in this class. So that will be coming up. All right, so kind of breaking down which lectures are relevant to which tasks. All right, for approximate analysis, we covered the portal method and beam approximation due to vertical loads in lectures 32 through 34. So that was the week before Thanksgiving break. And then the superimposing step, that is what we covered on Monday, right? So that's lecture 35. And we'll continue to talk about initial design today, but we started talking about that on Monday, so that's a lecture 35 reference as well. So we talked a little bit about this, right, where your stress in any given member is going to be a combination of axial stress and bending stress. So the equation for calculating bending stress that you can use is m divided by the section modulus, which is this capital S. So this is probably a new thing for you. You may not be familiar with it. until I mentioned it in class on Monday. But it is defined as the moment of inertia divided by C, where C is equal to half of the beam depth. All right, so this capital S is a property that is listed in these beam tables, so you don't have to calculate it, you can just look it up. That also means you don't have to calculate the moment of inertia. You don't have to do anything with the moment of inertia. Just focus on the section modulus, and then you can plug that in as your stress calculation M over S. A little bit easier than My over I, right? Because it's one less thing to keep track of. All right, so initial design continued. We have the wide flange shape, right? General designations shown there, and then I'm giving you an allowable stress of 34 KSI. So that comes from a yield stress of 51 KSI divided by a safety factor of 1.5. So using 34 KSI as your maximum allowable stress, you're going to determine an acceptable member size. And when I say member size, that means the wide flange section designation or shape is also used to refer to that. So W12 by 10 or whatever, not W12 by 10, that's going to be way too small. From the attached steel tables, those are attached in your project document. And this is where you get to choose your own adventure. You can either target a smallest depth or a lightest weight goal. All right, so these two goals are common, right? They're both commonly used in design, but they are at odds with each other, right? Because the smaller the depth, the more depth that you lose, the heavier the beam has to be in order to compensate for that loss of depth. So if you don't mind increasing the depth, you can select a lighter beam. Now, smallest depth is probably the most common goal because architects and clients like it because it gives you more floor to ceiling space, right? And that's something that people like a lot. But that might not be the most economic in the long run, right? So the lightest weight section might be cheaper. And so if that's more of a goal, if they don't really care about the floor to ceiling heights, then lightest weight would be ideal. So you get to pick. There's no wrong path there. And then this is an example of the tables that are attached in your project document. So it says see lecture 5 for an example that uses this table. We're going to go through that today. And you can see, all right, so I'll just show you since it's pulled up here. All right, so here are the shape designations. And remember, it's a depth by weight per linear foot is the designation. So the items that you're going to be interested in, you don't have to worry about the entire table, but you're going to want to pay attention to the area, the actual depth of the member, right? If your target is smallest depth, that's definitely something that you want to pay attention to. And then all of this you can ignore, right? From the after the depth to the end of this page, you can ignore. And then here, you want to focus on the S property in the strong axis orientation, right? So that's the XX axis. And that's the only column in this page that you need to think about. So everything else you can ignore. Please don't choose the S from the weak axis, right? That's not going to be correct. All right, so then last but not least, visual analysis. Most of what you need to know to complete the visual analysis portion of this project has already been covered in this class. But there are a few things that we'll need to touch on. So we'll get around to that on Friday. And as I mentioned earlier, right, once you have chosen your initial design based on your approximate analysis, you're going to use that size and assign it to all the beams and columns in your visual analysis model. Then you will run your analysis in VA, and look at the stresses in all the beams and columns to make sure that none of them exceed 34 KSI. If some of them do exceed 34 KSI, go to a smaller section or a lighter section, whichever way you're going, until you have found the smallest depth or lightest weight member that satisfies the design. Please don't try to model the three-dimensional structure, just the 2D interior frame. All right, so as a reminder, there are a bunch of documents to help you through visual analysis. Most of them were presented weeks ago in Lecture 15. So they're all in the Lecture 15 folder. I added this last one here that is specific to the final project. There might be a little bit of redundancy in that document with some things in the other ones, but it's going to be relevant to the final project. So we'll probably take a look at that on Friday as well. All right, any questions? Okay. All right, so with that, let's continue talking about the process of preliminary design. So as I mentioned last time, right, once you've done the approximate analysis, you want to superimpose those results, and that's going to be for columns, right, adding together lateral and vertical results for axial force, but for moment, for columns, that's just going to come from the Portal method, all right? For beams, axial forces will only be from the Portal method, and then the moments are what you need to add together from the vertical and lateral analyses, right? With shear, we only care about the shear from the lateral analysis for the purpose of getting the moment, right? Because that's how we obtain moments from the Portal method. So really you don't need to include this table or this column in the table if you don't want to. You can just list the axial and moment. All right, so then we also did a brief recap on beam stress due to axial and bending. So again, we can simplify that expression, right, to sigma is equal to m over s for bending, right? And so then we have our total stress is plus or minus p over a, and then plus or minus m over s. I'll say that's due to bending. All right, so now on to preliminary column design. So let's say you've gone through your approximate analysis, you have superimposed all the results, and you know your total axial force on the column. All right, again, that's going to be from your lateral and vertical loading. And then you also know the end moments of your column, and that's just going to be from the lateral, right, the Portal method. It's going to be the same magnitude at the top as it is on the bottom, and it's also going to be the same direction, right? For columns with loading left to right, that direction of your moments will be counterclockwise. So that means that this column, right, up here, let's look at the top end. Which side of this column will be in tension and which side will be in compression, just at the top end? Which one? Yep, very good. Yeah, so you'll have tension on the right side and compression on the left side. What about the bottom?
Opposite.
Yeah, it'll be opposite, right? You'll have tension on the left and compression on the right. So just keep that in mind, right? Because that's why we say plus or minus P over A, plus or minus M over I. And that's also why you only need to select the maximum moment value, right? So the maximum magnitude of moment from the, well, for columns, it's going to be one of the two ends, right? But for beams, you have 3 points to consider, right? The left end, the right end, and the center. So you only need to think about the maximum magnitude because whatever that magnitude is, right, it's going to be, if it's an end moment at least, it's most likely going to be either, if it's going to be positive on one end, it'll be negative on the other end, and then that same magnitude will add to the axial force, right? Whether the axial force is net tension or net compression. So it's important to keep track of tension and compression due to axial loads, and then also due to your moments that you're considering. All right, so back to focusing just on the column here. Although this approach applies to both beams and columns. Our goal, right, is to make sure that the stress that we calculate does not exceed the allowable stress. So in order to get there, right, we need to know what these properties are. So we will assume that the moment causes more stress than the axial force. And that's generally a safe assumption. All right, so we're assuming that M over S is greater in magnitude than P over A. So if we make that assumption, then we can determine the minimum size, the minimum section modulus that we need for the allowable stress, all right? So we'll set our stress equal to the maximum allowable stress and then solve for the minimum section modulus that we need. And if we have this scenario, right, if the bending stress contributes more than the axial stress, then our actual net stress distribution will look something like this, where we'll have the maximum stress at one end where the signs of the stresses are the same for axial and bending, and then a smaller magnitude stress at the other end, like that, with hitting a zero stress value somewhere right there, all right? So that would be your neutral axis location in this scenario. So then we have, or no, I take that back. The neutral axis is still here because it's only relevant to the bending stress. All right, so if you have axial stress is greater than bending stress, so I'll note that down here. All right, so if P over A is greater than M over S, then your stress distribution will look something like this, right, where it will be either all compression or all tension, depending on whether your net axial stress is in tension or compression. All right, so this particular stress distribution would be representing the top side of this beam, all right? The bottom side would have the reverse, where this side would be greater, all right? And then it would look something like that. So it's just things to keep in mind as you go through interpreting your results and presenting them. All right, so now we'll talk a little bit about preliminary beam design. So it'll be very similar to the column design, except now the values that you're adding together, right, are going to be combining the moments from vertical and lateral, and then your axial forces are just going to be from the lateral load. So you'll have your vertical loads on there causing your vertical moment, and at the center, right, at your midspan, that's going to be your moment, and it's going to be your maximum positive moment. There is no vertical component, or there is no lateral moment contributing to the maximum positive moment, right? Because remember, from your Portal method, moment is equal to 0 at the center, whereas from vertical loads, your moment is maximum at the center. And then your negative moment, right, your maximum negative moment is going to be the value from the Portal method plus the end moment that you calculated from these vertical loads. So here, that's really all you need to think about. You want to check both, right? Make sure that you check both and use the largest magnitude. All right, any questions? Okay. All right, so now we'll go through an example. So let's say we have a beam or column. It doesn't actually matter if we have identified the maximum axial force and the maximum moment acting on that column. These are the values that we will use. If the allowable stress is 20 KSI in this problem, and we're looking for the smallest depth member that meets the design criteria being not exceeding the allowable stress, then this demonstrates the process that we will go through. So this is going to be an iterative process, as you will see, and this is what I would like to see you present in your calculations for final project. So we'll make that assumption that the moment contributes more to the stress than axial force, and we'll solve for the minimum required section modulus. So that's going to be our moment of 150 kip feet, and make sure that you apply appropriate unit conversions. This is a common mistake that folks make in this step. And then you end up with a much smaller size than what would actually work. And so in doing that, just convert the moment from kip feet to kip inches, right? Don't convert the allowable stress to KSF. Technically you can do that, but that's really not how we tend to do things. So this will give us a minimum section modulus of 90 inches cubed. So then from the beam tables, right, we're gonna pick a size. So I'm gonna go, if you have your project document handy, you can look as well. I think it will be the third page in the, so the middle page of the tables. We're gonna start there because we're gonna be first looking at a W12 section. So you can see in these tables, right, they're organized in decreasing depth. So the first table has a W21, and that's not the largest size available, but I decided to restrict the range for you guys so that you don't go way too far off base. And so W21 down to W18s on the first page, and then W16s and 14s, and then 12s. So the 12s start on the third page of the tables, and we're going to focus on this section property here. So I'm going to box that column so that we can quickly see back to the right place. And we said 90 inches cubed was the minimum, all right? So scanning down these W12s, we can get down to the last two entries. And so this one right here is the lowest one that is at least 90. So we will start with that one. And this is a W12 by 72. So the nice thing about these tables, right, on this page, you can just go to the right, the leftmost column, and that will give you the weight per linear foot. All right, so you know you're looking at W12s, and this one is a 12 by 72. So then what we want to do is note the actual S value, all right, so the 97.4, and note the actual area, all right, so that's the first column in the table to the right of the designation. So that's 21.1, and the actual depth is 12.3. All right, so that's just for our keeping track of what is the smallest depth member we can find. All right, so now we'll go back with that information to our example here. All right, so the actual S is 97.4, and the actual area is 21.1. And I'm going to note here that the depth is 12.3 inches. And that is for a W12 by 72. All right, so now we can check the total stress, right? So our actual stress is going to be P over A plus M over S. So that's 100 kips divided by 21.1 square inches plus 150 times 12 divided by 97.4. And that gives us 23.2 KSI. That exceeds our maximum allowable stress, so this section is no good. We have to go to a greater depth section to find something that'll work. So the next one up from the table, you can verify this on your own. I'll save time and not keep going back and forth to that table. We'll try the next one up, which is a 12 by 79. So that one has an S of 107 and an area of 23.2. All right, repeating the calculation, we would get a normal stress of 21.1 KSI, which is still not good enough. So we'll keep trying. Try a 12 by 87, which would be the next one up in the table. That has an S of 118 and an area of 25.6. So the normal stress here is 19.2 KSI, which is less than or equal to 20. So that works for us, all right? So we found a W12 size that will work, but the problem statement didn't say the smallest depth W12 member, it just said the smallest depth member. So we should, to complete our due diligence, see if there isn't a smaller depth member in the W10s that might work as well. So now I'll jump back to the tables. All right, so this is the page we were looking at before. On the next page, we see some more W12s. We know those won't work, but let's look at the heaviest W10s and see if something might work there. So here, again, we'll look at the the S property. We have some that are high enough, right, that they look like they might work. So let's see if a W10 by 100 will work with an S of 112, right? So that's a little bit smaller than the one we just found to work for the W12s. We got an S of 118 to work, but we have a larger area, right? So we might be able to pull this off. Let's see. And then let's also make note of the depth, right? So our depth here is 11.1 compared to the W12 by 87 where the depth is 12.5. So these sizes are smaller in depth, right, than a W12. So it's worth checking. So a W10 by 100 has an S of 112 and an area of 29.3. So this gives us a normal stress of 19.5 KSI, which also works. All right, now remember, even though this 19.5 is closer to 20 than the 19.2 before, that doesn't matter, right? It doesn't matter necessarily how close you get to 20. What matters is it the smallest depth section that will work? And in this case, it happens to be both. So since our depth, I'll note here, right, depth is 11.1 inches, whereas with this one, the depth was 12.5 inches. All right, so this one is the one we want to pick for the smallest depth section that works. But I wanted to emphasize that, right, because in your final project, you might find a smallest depth section that works, right, but maybe the normal stress is significantly lower than the other section size that you checked that also works, right? If you're looking at comparing like W14s and W12s or W12s and W10s. So it's not necessarily who gets the closest to 20, right? It's which one can get the closest to 20 but also have the smallest depth, right? So the smallest depth takes precedence. And then if you're taking the other path and looking for the lightest weight, you would go in the other direction, right? You would want to start with maybe W18s and see if you can get what's the lightest weight W18 that you can find, and then check the ones above and below to see if there's a lighter weight section that you can identify that works, right? So I'll just note, we don't have time to go through it today, but if you want to practice that method on your own, I'll just note here that for this example, if you want to check for lightest weight, you'd want to look at W14s, 16s, etc. And in this case, you would find the lightest weight section to work would be a W16 by 77. All right, for an S of 134 and an area of 22.6. This one gets a normal stress of 17.86 KSI. All right, so even though that value is not as close to 20 as some of the other lightweight sections you might calculate, it is the lightest section that still does not exceed the allowable stress, and that's what you want, okay? All right, questions? Very good. Well, thank you for your attention, and I will see you on Friday. We'll talk more about the project and focus a little more on visual analysis.